Pac-Man is a completely deterministic game. As shown in my last video on the game, all of the ghosts' movements are based off of where Pac-Man currently is in the maze. Therefore, with the right knowledge, you can predict exactly where any of the ghosts will move at any time. Or can you? When Pac-Man eats a power pellet, the ghosts become frightened and seem to move in a random, unpredictable pattern. This is the only time a random number generator is used in the game, to determine which direction a ghost will turn at an intersection in the maze while frightened. While still deterministic, it is the only non-predictable element of Pac-Man. This video will go under a deep analysis of the game's RNG function, and how the ghosts tend to behave in this situation. We'll find that frightened ghosts do tend to gravitate towards a certain section of the maze after all. The random number generator, or RNG, is responsible for, well, generating random numbers. The processor running the game's code doesn't have a little coin to flip or a dice to roll to get any source of randomness, so this feature has to be programmed via software. And it turns out that writing a program or function to come up with numbers randomly is quite difficult. You could argue it is impossible. Writing code to generate random numbers is essentially like creating a list of instructions on how to calculate a certain value. In that case, it isn't truly random. It's still deterministic. However, the end result looks random enough that it can be treated as if it really were random. Pseudo-random, if you will. Pac-Man has a very basic RNG function, but with a twist. There is a 16-bit value in memory that is treated as the RNG index. This is set to 0 at the start of the game and at the start of each level. This index is used as a seed value to generate the next index, which overwrites the old one. For example, the very first index generated is the number 1. The RNG function takes the number 0 as its input and outputs the number 1. Then, the next time a random number is needed, it uses the number 1 as its input. In this case, if 1 is its input, the output will be the number 6. Like I said, the rule is very simple. We take the input index, multiply it by 5, and add 1. That's it. Well, and also modulo by 8,192, which just means if the result is greater than 8,192, divide it by 8,192 and then take the remainder. For example, the 8th RNG index is 7,544. If we multiply that by 5 and add 1, we get 37,721. Divide that by 8192 to get 4 with a remainder of 4953. So the 9th RNG index is 4,953. This function does an alright job at generating random numbers. There are times where it's quite obvious what the pattern is, especially at the start with 0, 1, 6, 31, but most of the time it's fine. What's important though is the distribution of the numbers. Are all numbers equally likely to be generated? It turns out that yes, they are. At least all numbers less than 8192, of course. This function will run through all 8,192 numbers between 0 and 8191 before it repeats. The last number in the pattern being 4,915. This is a good quality for an RNG function to have, since it means that there is no bias towards certain outputs, at least at a single random access. There may be strong correlations if you want to generate more than one random number at a time, but that's not going to be a problem for us for multiple reasons. However, notice that I have been calling these RNG indices and not the RNG outputs themselves. That's because this index is not the true output of the function. It's just a helper value that is used to create the output. This index is used as an offset into the game's code to grab a single byte. That's the output. It's not an index into a table of any sorts either. The first 8,192 bytes of the assembly code of Pac-Man is used as the RNG output. Most of the bytes here are machine code that represents the assembly instructions that make up the various functions in the game's code, none of which have anything to do with random numbers. Here's an analogy. Suppose you were told to come up with a random English word. It would be like using the same function for the index here, but then using that index to look up a word in your favorite book. If your input index was 6,189, you'd calculate your output index to be 6,370. So you'd find the 6,370th word in the book. While this method of looking up a byte definitely removes the correlation between successive random numbers, it impacts the uniformity of the output. I mean, imagine how much more likely you are to randomly pick the word "the" from your book. Here is a chart that displays how many of the each 256 different bytes there are in the first 8 kilobytes of the game's code. As you can see, this is hilariously non-uniform. For a uniform distribution, each number should appear 32 times. However, 0 appears over 600 times. That's because there's some empty spaces in the code, which are just filled in with nothing but zeros. The number 77 also appears a lot, even more than 0. This is because this corresponds to the byte hex 4D, and the memory region from hex 4D00 to 4DFF is where most of the game's main variables are held. So each instruction that wants to read or write to any of these variables is going to make the byte hex 4D show up in the code. Some numbers just don't show up at all in the first 8 kilobytes, like 65, 141, 146, and 186. Now, this may look bad, but fortunately there's a catch that almost saves this. The only reason the RNG function is used is to determine which direction a frightened ghost moves at an intersection. Well, there's only 4 possible options: up, down, left, or right. This can be represented with only 2 bits. The actual mapping of these bits to directions is 0, 0 for right, 0, 1 for down, 1, 0 for left, and 1, 1 for up. Because of this, the only part of the output of this RNG function that's really important is the bottom 2 bits. So let's regroup all of these outputs based only on their bottom 2 bits. Okay, that's a little better, I guess. I mean, the last distribution set a really low bar to beat. You would expect a uniform distribution to output each of the 4 options 2,048 times out of 8192. While the 00 bits corresponding to right are almost there, the others are just way off. The bits 1, 1 corresponding to up are only 1,338, which is just 16.3% of the total. This is one of the 2 flaws of the frightened ghost's behaviors. The RNG function that governs their movement is not uniform. The directions left and down are heavily biased for, while up is very heavily biased against. So you'd think this would mean the ghosts would just favor the bottom left corner of the maze then, right? Well, not so fast. Real quick, in case you're interested, here's the RNG function itself. Only 13 assembly instructions. That's how you know it's simple. Here is where the old index is loaded into the CPU. The index gets multiplied by 5 here, and incremented by 1. Here's the modulo by 8192, done by logically ANDing the upper 8 bits of the index with hex 1F, essentially truncating the index to 13 bits. That index is used to grab a byte from the game's ROM, and then the new index is stored to memory, overwriting the old one. It's unfortunate that this function is found at hex 2A23 in the game's code, outside of the reach of the RNG index, which is limited to hex 1FFF. Which means the bytes that make up the RNG function can't be themselves the output of the RNG function. So the frightened ghosts use the RNG output to determine which direction to move at an intersection. What if they can't physically move in that direction? Suppose a ghost was at this intersection, but the RNG told the ghost to move up. There's a wall there, so what happens now? Instead of generating another random number, the ghost will just try the next direction in a clockwise order. In this case, the ghost will instead try to move right. But oops, ghosts can't turn around 180 degrees either. This ghost approached the intersection from the right, so it can't choose to go right here. This direction is no good, and it tries the next direction. It tries moving down next, which is actually a valid direction to move. This results in a very biased decision. If the ghost were to roll an RNG value that corresponds to up, right, or down, they would all correspond to going down. The only way a ghost can go left at this intersection, if they are coming in from the right, is if left is chosen from the start. According to the chart we made earlier, this would be a 29.9% chance. This leaves a whopping 70.1% chance for the ghost to choose to move down. This is the second flaw of the frightened ghost's behaviors. The allocation of random numbers to directions is not uniform either. We can use this information to create a table of probabilities for each intersection type. Since the RNG is biased itself, none of these situations are symmetric at all. First, it's worth pointing something else out right now. Frightened ghosts don't call the RNG at just the intersection tiles in the maze. They call the RNG every time they move from one tile to another, even well inside the tunnels. Since the ghosts are blocked by walls on two sides, and they can't turn around 180 degrees, there is only one valid direction to move. This is actually somewhat notable because by calling the RNG function even in these trivial cases, it changes the RNG index value. This can help with shuffling up the index to prevent any noticeable patterns from emerging, say by observing which directions ghosts are moving to predict which directions will be chosen next. But anyway, there are 6 types of tunnel tiles, 2 straight tunnels and 4 corners. For each of these tiles, a ghost can enter it from 2 different directions, which results in 12 possibilities. These 12 cases can be grouped into 4 sets, one where right is the only valid option, one for down, left, and up as well. Trivially, even though the distribution of random numbers results in this sort of distribution of directions, the only valid direction is straight forward, and a ghost has a 100% chance of continuing in the direction it was already moving. Where it gets interesting is the 3-way intersections. There are 4 types of 3-way intersections, and a ghost can enter from one of the 3 sides, which results in 12 more different cases. These can again be split into sets corresponding to which 2 directions are actually valid. There are 6 of these sets, and this is what the likeliness of a ghost turning in each direction is. Now, the 2 sets that are split between 2 opposite directions aren't too bad. This is because each direction picks up the weight of one of its neighboring directions. The most fair case is when a ghost has to pick between moving up or down. A random direction of left or up results in a 46.3% chance of going up, while a random direction of right or down gives a 53.7% chance of going down. The other 4 sets for picking 2 adjacent directions are ridiculously lopsided though. They're all basically 3-to-1 odds for picking one direction over another. The worst offender is left versus up. A frightened ghost only has a 16.3% chance of choosing to move up. Finally, we have the 4-way intersection, of which a ghost can enter from all 4 different directions. Here's what those distributions look like. In all 4 cases, it is about twice as likely that the ghost will turn left from its perspective in the maze. This is because the only invalid direction is doing a 180 and backtracking. This gets rotated 90 degrees clockwise, which corresponds to turning to the ghost's left. Now, how can we use this information to figure out where the ghosts are more likely to go? I know this isn't a very practical question, since ghosts don't get around very much while frightened, and in the later levels they don't become frightened at all, but I think it could be a fun exercise. The best way to analyze this problem, in my opinion, is with a Markov chain. If you don't know what a Markov chain is, here's a quick overview. Suppose you have some sort of process that can exist in one of several states. We can represent these states as a set of vertices in a graph. So here we have 3 different states, A, B, and C. And in this process, at every step in time, the current state can change. The probability of changing into a different state is determined strictly by the current state. Let's say if you are currently in state A, you have a 50-50 chance of switching to state B or state C. We can represent these state transitions as weighted directed edges in this graph. Similarly, if you are in state B, you may have a 30% chance of changing to state C, 60% chance of changing to state A, and even a 10% chance of staying in state B. We represent this with a self-edge from B to B, and so on. This is a Markov chain. We can sort of simulate an instance of this process here by, say, starting in state A, and then moving from state to state based on the probabilities denoted by the edges coming out of the node of the current state. Just do this like a million times, and then tally up how many times each state was visited, and you can find the average time spent in each state. With a really large graph, this can take exponentially longer to converge on meaningful value though, so there's a better way to do this. We can start with a mass of 100 on state A, and then divvy up the mass proportional to the outgoing edges on each vertex. In this case, 100 gets split up 50-50 to both states B and C. This leaves state A empty with 0, since states B and C were previously empty. Then, on the next step, state A has 0 mass, so it doesn't give out anything. State B gives 60% of its 50 to state A, 30% to state C, and keeps 10% to itself, while state C gives 30% to state A, 50% to state B, and keeps 20% to itself. With this step, now state A has a mass of 45, state B has 30, and state C has 25. Keep stepping through time like this, and eventually the numbers will converge on a steady state fairly quickly, as long as the chain is a special kind of chain known as ergodic, which isn't important to explain in this video, but you can look up more about it if you're interested. The fun thing, though, is that if the Markov chain is ergodic, then this is the steady state of the chain. It doesn't matter what the initial conditions were. We started with a mass of 100 on state A, but we could start with a mass of 100 on state B or state C, and we would arrive to the same steady state. So what we can do is build a Markov chain that represents each intersection in the Pac-Man maze as a vertex in the graph, and then the edges will be the paths between them. The weights of the edges will be the biased probabilities that I showed earlier. Then we can plop down a mass of 100 frightened ghosts anywhere in the graph and iterate the whole thing over and over until we reach a steady state. This will essentially give us a heat map of where the frightened ghosts like to hang out in the maze. So let's do it. It shouldn't be too hard. Since the tunnels between the intersections are somewhat superfluous, I'll omit them at first. I'll add them back in later once we understand what's going on and we know everything is working properly. First, we can make one vertex in our graph for each intersection in the maze. We'll need 2 edges for each path between them, one for each direction. Then all we need to do is fill in all the edge weights with the RNG direction probabilities, right? Well, not so fast. Let's look at a single intersection. This vertex has 3 edges coming out of it, representing the 3 directions a ghost can move out of this intersection. But we know that a ghost cannot turn around 180 degrees. When a ghost enters a 3-way intersection, it really only has 2 choices to go, not 3. This is because we haven't captured the entire state of a ghost within our vertices. Not only do they need to represent the position of the ghosts within the maze, they also have to encode which direction they are traveling to. This means that each intersection in the maze needs a set of vertices corresponding to it, one for each direction the ghost can approach the intersection. 3-way intersections will have 3 vertices, and 4-way intersections will have 4 vertices each. I'll put little arrows inside to make it clearer. Now we can hook up the edges properly. If a ghost is approaching this intersection from the right, this will be represented by this vertex, since the ghost is moving left. If approaching from the left, this vertex, and approaching upwards, this one. Now the outgoing edges. If the ghost is approaching upwards, it can go either left or right. From the left, it can continue moving right or go down. And from the right, it can go down or move on to the left. Now we can apply the edge weights with the percentages calculated earlier. A ghost entering this intersection from the right can go left with a 30% chance and down with a 70% chance. And so on. You get the idea. You can also see that having these intersections split into multiple vertices allows the different approach directions to affect the direction probabilities. Here, the ghost has a 70% chance of going down if entering from the right, but if entering from the left, it only has a 29% chance. We just have to break down each intersection like this. This is a lot more complicated, but this is due to the restriction that the ghosts just can't go backwards. Now, before we calculate the steady state, we need to add the straight paths back in. We can't just ignore them completely because the distance between every intersection isn't equal. A ghost will spend a longer time in a longer path, like those at the bottom of the maze, simply because they take longer to traverse. So what we really need to do is represent each tile in the maze as a set of vertices, not just each intersection. This is pretty trivial to do, since a ghost can only move forward in a tunnel. Each tunnel tile will have two vertices associated with it, one each for what direction the ghost is moving. Then, we just connect each of the directions together with a probability of 1. Essentially what this does is forwards all of the ghosts that turned a certain direction at one intersection to the next intersection without allowing them to turn around. It also delays them from reaching the next intersection proportional to the length of the path between the two intersections. But now we can finally simulate the frightened ghost's behavior with this behemoth of a Markov chain. For the sake of this video, I'm going to simplify what this graph looks like. Since we are ultimately interested in where the ghosts are in the maze, we don't really need to know what direction they're moving. Therefore, I'm going to take all of the vertices that correspond to each tile and group them up into these meta-vertices. The mass of these meta-vertices is just the combined mass of the vertices inside of it, which represents how many ghosts are currently on this tile, regardless of what direction they're facing. And I'm not showing the edges of the graph anymore because it's pretty intuitive that adjacent vertices in the maze connect to each other. Now, instead of plopping down 100 ghosts in a single tile, I'm going to put 50 ghosts each on the two tiles right by the ghost house. For each tile, 25 will be facing left and 25 will be facing right. If you know why this might be important or want to give your best guess, post about it in the comments. Anyway, here we go. The ghosts slowly disperse throughout the maze. Since I picked 100 ghosts, the mass for each tile represents the percentage of the time you will find a frightened ghost on said tile. You're more likely to find a ghost at an intersection as opposed to a tunnel, just because there are more ways to approach those tiles, but you might be able to see that there is another pattern appearing. The distribution appears not to be symmetric at all. I know at the start I said to hold on, that the ghosts might not favor the bottom left corner of the maze, but it turns out that is exactly the case. In fact, a frightened ghost is 6 times more likely to be found in the bottom left as opposed to the top right. That is, if given a large enough amount of time, which is way longer than you would ever experience in-game, but hey. Now, what is the root cause for this bottom left bias? Remember, there were 2 flaws to the ghost's behavior. With this Markov chain, we can tinker with the probabilities and separate and isolate those 2 different properties and see what kind of effect they have. First, let's start with fixing both problems. Here, I'll set the probabilities of choosing a direction to be a perfect 50-50 split at all 3-way intersections and a perfect 1/3 chance for each direction at a 4-way intersection. Simulating this maze, we see that the distribution of ghosts is pretty much uniform. Like I mentioned before, ghosts would be more likely to be at an intersection just due to having more ways to approach the tile. This also shows that one of those 2 flaws is definitely the culprit. Let's fix the RNG function first. Here I'll change the probability of a ghost rolling one of the 4 directions to be a perfect 25% chance each. The ghost will still pivot that option 90 degrees if it would move backwards or turn into a wall, meaning that some intersections are still split 75 to 25. It looks like the ghosts still prefer the bottom left corner, but not by as much. This sort of makes sense. Yes, the method of pivoting the direction to take is heavily biased to turning left, but it is rotationally symmetric. Each biased movement rule is part of a set of 4 rules that are 90 degrees apart from one another, and they should all cancel out over time. The only reason they don't completely cancel out is because the maze itself isn't 90 degrees rotationally symmetric. This produces small biases in certain locations just due to the shape of the maze itself. Now let's see if we can isolate the other variable. In this case, I kept the biased RNG function, but removed the rule about pivoting the direction. If the ghost rolls a direction that would make it hit a wall or turn around backwards, it rolls again until it picks a valid direction. Aha! Here's the culprit. In fact, this ends with an even worse distribution than the unmodified version. The pivoting mechanic allows for a chance to break free from the bias of the RNG function. For example, at this intersection, since a ghost approaching from the left can't go back to the left, normally, if it rolls a left, it will end up going up instead. Even though up has the worst odds on its own, the fact that left is blocked practically triples the probability that a ghost will turn up here. Without this boost, a ghost only has a 23% chance instead of a 46% chance of going up. This makes it very unlikely that a ghost will hang out at the top of the maze for any substantial amount of time in these circumstances. Finally, I just want to make sure, is this all accurate? Markov chains are cool and all, but was this a proper way to represent the behaviors of the frightened ghosts? Well, there's only one way to find out. Instead of simulating in a sandbox, let's try running the actual game. Only a minimal amount of tinkering with the game will make this easy to test. Just force the ghosts to always be frightened and move Pac-Man out of bounds so that he can't eat any of them. Then I'll just let the ghosts do their thing and sample their positions every few minutes or so. Speed up the game as fast as I can make it go, and have it run for hours. After recording thousands of data points of where the ghosts are, we can plot a heat map out of it. And here's what my results were. And hey, that's shockingly similar. It turns out math is useful after all. But is it really? The only way we can realize this bias is by making the ghosts frightened for way longer than they were intended to be. In reality, the main factor that determines where a frightened ghost is in the maze is where the ghost is when Pac-Man eats the power pellet. I think the more meaningful rule to come away with is this. Frightened ghosts prefer to turn left from their point of view. The only exceptions to this are when they are moving to the right into a wall, where they will slightly prefer turning to their right to go down, and when they are moving downwards into a wall, where they will slightly prefer turning right to go left. And then, ultimately, none of this information matters at all in the later levels, since ghosts overcome their fears and no longer become frightened even after a power pellet is eaten. Thank you for watching. This episode of Retro Game Mechanics Explained was made possible by supporters of the channel via Patreon. If you would like to help support the video making process, you can become a patron for as little as $1 a month. Patrons get early access to videos, as well as behind-the-scenes content, such as creator commentary. I appreciate every little bit I get, so thank you.